Do you like Sudoku? I like Sudoku. Okay. Later. So the distribution here, what's the shape of my distribution? It is right skewed. The author completed a Sudoku puzzle in 3 minutes and 19 seconds, and that puts him in the top 19%. Okay, so we're talking about the location of individual observations in a distribution. All right, so we have what is called the percentile. Percentile of a distribution is the value with p% of the observations less than it. Okay, note that percentile does not mean percent correct. Percentiles are also whole numbers. Okay, so if we get a decimal, we're going to round. And I am sure you should be familiar with percentiles, right? We have things like top 10%. All right, looking at GPAs. When you take a standardized test, for example, and you get a score, that score may be, in addition to the raw score that they give you, it may be expressed as a percentile, right? So like when my children take a math test, they get a reading percentile, meaning that they're at a certain percentile in relation to all the other kids that took the same test that are the same age. Okay, so the stem plot below shows the number of wins for each of the 30 Major League Baseball teams in 2012, where 6/1 represents a team with 61 wins. Find the percentiles for the following teams. The Minnesota Twins, who won 66 games. Okay, so 66 is right there in the stem plot. There are 1, 2, 3 teams that won less games. There's a total of 30. Okay, so we're going to say 3 divided by 30 gives me the 10th percentile. So we're looking at the observations that are lower than the score that you got. So 10th percentile because 3 out of 30 teams had less wins. Okay, the Washington Nationals, who won 98. Okay, that's the highest one there. So there are 29 out of 30 teams that had less scores. All right, so dividing that, and then I'm going to round it. So we're going to say the 97th percentile. Because 29 out of 30 teams had fewer wins. If it says interpret, then yes. Okay, if it doesn't say interpret, then no, not necessarily. All right, and so the last one, the Rangers and the Baltimore Orioles, they both won 93 games. Okay, so theirs is right there. You're going to count the number of teams that had less wins. And so if you count those up, I think you should get 22. So it's 22 out of 30, which if you divide that and round, you should get the 73rd percentile. Because 22 out of 30 teams
Attendance, please.
had fewer wins. You count the number of observations that are lower. Okay, so this is a stem plot where 6/1 means 66. So if I'm looking at this 66, there's a 61, a 64, and a 55 with the fewer ones there. Does that make sense? And so it's always the number of observations that are few. All right, well, turn the page there. Let's look at the second page. And so we have what's called a cumulative relative frequency graph. All right, we have already seen a relative frequency graph, but this is a cumulative relative frequency, okay? So we are looking at the distribution of median household incomes for the 50 states and the District of Columbia in a recent year. All right, so we have 35 to 40 and thousands of dollars. 35 to 40,000, there was one state where the median income was in that range. And then 40 to 45, there were 10, 45 to 50, there were 14. Okay. Here in this column, they're expressed as percentages. All right. And so what a cumulative relative frequency does, the first one is the same. Okay. But then it's going to add these two together to get 11. And then it's going to take 11 and add 14 to get 25, and then add 12 to get 37. So it's looking at the total number of observations up to that point. Does that make sense? Okay. And obviously the last one has to be the total out of the total, expressed as a percent, so 100%. And so here we have a graph with the median household income on the x-axis and the cumulative relative frequency on the y. And so let me read through this right here. It says the point at 5049, so that is that point right there. The point at 5049 means that 49% of the states had median household incomes less than $50,000. The point at 55.725 means that 72.5% of the states had median household incomes less than 55,000. So subtracting those two percentages, 23.5% of the states had a median household incomes between 50 and 55,000 because the cumulative relative frequency increased by 0.235. Okay, and if you notice, if you look at there, it's not quite 0.235. I believe it's 0.236, but that's just a round difference. Yeah. All right, so let's enter the questions here. It says use the cumulative relative frequency graph for the state income data to answer each question. At what percentile is California with a median household income of $57,445? So I'm going to go to approximately 57,445 on the graph, which let's say it's like right there. All right. And so then I'm going to go over there to look at the percentage. So I said California was about the 78th percentile. Or 80th percentile. I mean, as long as it's reasonable and it's close, I would take that. Okay. Meaning, will that just go away? Huh. So about the 78th percentile, meaning that about 78% of the states in the District of Columbia have a median household income less than California, which makes sense, right? If you think about the cost of living in California is very high. Okay, so they should be at a higher percentile there. Part B says estimate and interpret the first quartile of this distribution. So the first, let me write down the interpretation. The first quartile is the 25th percentile. So about, in the context of this problem, about 25% of the states have a median household income less than so that's my interpretation. And now I'm going to look at the graph and go to about 25%. Let's say it's right there. And so as long as it's close here, I said less than $45,000. Okay, and the last thing here, you made the connection between the percentiles and the quartiles. Okay, so they're just wanting you to link what we did in the last chapter with the 5-number summary. Q1 is at the 25th percentile, and the median is at the 50th percentile, and Q3 is at the 75th percentile. Okay, percentiles are fairly straightforward. I think most students are used to working with them. What is probably new is what we're going to do next, which is a standardized score. All right, so take a look at that. Why do we standardize observations? Well, let me give you an example. Let's say somebody goes and takes the ACT and they make a, let's say they make a 27 on the math. All right. And then they go and take the SAT and they make 630 on the math section. Well, on which test did they do better? Well, how do we know? Well, the answer to that is we could figure that out, and we do that using a process of standardization. Okay, and so the answer to the question, why do we standardize observations? We do that in order to make comparisons. So we have what is called a standardized score, or a z-score. If X is an observation from a distribution that has a known mean and a known standard deviation, then the standardized score for X is Z equals X minus mean over the standard deviation. This is also known as a z-score. A z-score tells us how many standard observations from the mean and observation falls, and also in what direction. Observations larger than the mean have positive z-scores. Observations smaller than the mean have negative z-scores. Okay, so let's go back to the example with the baseball. In 2012, the mean number of wins for teams in Major League Baseball was 81, with a standard deviation of 11.9. And this says find and interpret the z-scores for the following teams. Okay, so we have the New York Yankees, also known as the Evil Empire, with 95 wins. So we're going to find the z-score for the Yankees. Okay, so again, z is X minus mean over the standard deviation. All right, so for the Yankees, they had 95 wins. We're going to subtract the average, which was 81. And then divide by the standard deviation, which is 11.9. And obviously, since they had more wins than the mean, our z-score is going to be positive. So take your little calculator And calculate the z-score really quick. 95 minus 81 divided by 11.5. And what'd you get? Somebody? 1.18. Okay, so this means the New York Yankees in 2012 were 1.18 standard deviations above the mean. Okay, that was the interpretation. Okay, so let's do the same thing for the Mets. The Mets had 74 wins. And this time I know my z-score is going to be negative because it's below the mean. So I've got 74 minus 81 divided by 11.9. That gives me negative 0.59. And the interpretation. So the Mets were 0.59 standard deviations below, and I don't remember, below the Mets were 0.59 standard deviations below it. Okay, so here's what z-scores allow us to do. The single season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 61, Mark McGwire hit 70 in 1998, and Barry Bonds hit 73 in 2001. In an absolute sense, Barry Bonds had the best performance of these 4 players because he hit the most home runs in a season. However, in a relative sense, this may not be true. Baseball historians suggest that hitting a home run has been easier in some eras than others. This is due to many factors, including quality of the batters, quality of the pitchers, hardness of the baseball, dimensions of ballparks, and possible use of performance-enhancing drugs. To make a fair comparison, we should see how these performances rate relative to those of other hitters during the same year. So here's what I want you to do. Take these 4 guys and compute the z-score for each one of them. All right, do that for me, please. And we're going to see which one had the best performance. Okay, so calculate those for me. What was Babe Ruth's z-score? 5.44. Okay. Roger Maris, 3.15. Okay, Mark McGwire, 3.88 is z-score. And then Barry Bonds, 3.91. So in relative terms, who had the best performance? Babe Ruth had the best performance. Babe Ruth had the best performance. Because he has a Z-score of 5.44, meaning he was over 5 standard deviations above the mean. Okay, and so here's what we're going to look at. Not now, but next Tuesday, all right, is if a distribution is normally distributed, which we will talk about that, okay? Over 5 standard deviations above the mean is extremely, 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 extremely rare. Okay, so this is a fantastic performance by him. He had 60 home runs in a year where the average number of home runs was 7. Okay, that is a bit of an outlier, yes. Okay, and an extremely rare occurrence for anything to be more than 5 standard deviations above the mean. So now, Thatcher, my joke, it's on the timeline. You can read the little cartoon. Mhm. Did we not get our timelines? Mhm. I hope you don't expect me to come up with a stats joke like every day. I mean, maybe once a week.
I was not getting this.
I mean, but now you can tell your significant other. The joke was subpar, is that what you're saying? All right, we need to look at one last thing here. Okay, here we go. Last thing, last page. It is common to transform data, especially when changing units of measurement. It's important to know how the transformation affects the mean, median, and standard deviation. So let's look at the effect of adding or subtracting a constant. So look up here for a second. Let's say I grade all your tests, and this is the range. This is the lowest test, this is the highest test. And I can calculate the mean and certain other data points. What would happen, hypothetically speaking, this will not happen, right? But let's say I'm going to add 10 points to everybody's test. What would happen to this distribution? It does this. So the highest score would be the highest score plus 10, and the lowest would be the highest plus 10, and the mean would be, it would go up by 10, right? Does the shape change?
No.
No, it doesn't. Okay. Well, what would happen, hypothetically speaking? Let's say, you know what? Every once in a while, the supreme statistical dictator has moments of generosity. I'm just going to double everybody's test score. All right. So you made 15. Well, now you got 30. All right. And you made 25. Now you got 50. Okay. Now we're not changing each score by the same amount, right? We're changing it by a factor of 2. So what would happen to the mean of that distribution? What would happen to the shape? That's what we're going to look at. Okay.
To me, it just feels like it would just like exaggerate the shape.
Well, let's look and see. It says, here's a graph and table of summary statistics for a sample of 30 test scores. The maximum possible score on this test was 50 points. So what's the shape? Number one.
Left skewed.
It is. Do I want it to be left skewed or right skewed?
Right now, that's wrong. You want
I want it left skewed, right? Because I want more people with higher scores. Okay. So suppose that the teacher was nice and added 5 points. Well, it's too bad for you guys that you don't have a nice teacher. I don't add points. No, never. Sorry. Okay. So how would this change the shape, center, and spread of the distribution? Here are the graphs and the summary stats for the original scores and the +5. Okay, so notice, okay, the mean went up by 5. The Q1, the median, everything went up by 5. Did the shape change?
No.
It did not. It stays the same. What about the center? It increased by 5. Increases by 5. And the spread, it also stays the same. Okay, if I'm adding
The
5,
spread is two numbers, right? The range stays the same, but the spread is both the low and high spread.
the range is the difference between the highest and the lowest. Okay, the spread
It's like it's some-
is how far
So the
spread out they
yeah,
are.
So both the lowest number, because the spread is two numbers, right? Like it's, in the first one, it would be 12 to 48, and then the second one, 17 to 53. So both, does that make?
I think you're overthinking that.
Okay.
This stays the same. In other words, saying, look at, he has an important question here, so let's look at it. Look at the top distribution and the bottom distribution. Is one more spread out than the other?
No.
No, therefore the spread stays the same. Okay, well, suppose that the teacher in the previous alternate example wanted to convert the original test scores to %. So the first test was out of 50, so we're going to multiply everything by 2 to make it out of 100. Here are the graphs and the summary statistics for the original scores and then the doubled scores. Okay, so notice if we multiply everything by 2, the mean is multiplied by 2, the standard deviation is doubled, the mean, the Q1, the median, everything is double. Okay, what happens to the shape? It still stays the same. It's still left skewed. It is more spread out now. The center is multiplied by 2. And the spread is also multiplied by 2.